This is Algebraic Reasoning, Chapter 2.2, Exercises 13 through 23. This exercise set has to do with transformations of quadratic functions. I'm going to do mostly odd number problems, but you're going to see some little variations in this set for reasons I'm going to explain later. For questions 13 to 17, identify the domain, range, x-intercept, y-intercept, and vertex of each quadratic function. Write the domain and range in three different ways: as an inequality, interval, and in set builder notation. And so what I'm going to do first is the domain and range. So domain, and I'm going to use inequality notation first. And for inequality notation, we put x in the middle, and x is going to be greater than negative infinity, but less than infinity. So another way of saying this is all real numbers. Our range in inequality notation is going to be, well, we have a maximum where x equals 6, and that maximum is -1. And so we put y in the middle, as we did for x, and y is greater than negative infinity, but less than or equal to -1. So that's our inequality notation. Next, I'm going to put the interval notation. And I think what we're doing here is trying to get used to the different ways of describing a domain and range. And in interval notation, I put this big D as an abbreviation for domain, which I plan to do for the rest of this exercise set. So we have x is greater than negative infinity, but less than infinity. And our range is going to be greater than negative infinity and all the way up to -1. And since -1 is included as part of the range, we're going to, instead of parenthesize, we're going to bracketize that. So that's our interval notation. And lastly, set builder notation. And set builder notation to me seems a little more obscure, but they're trying to expose you to a variety of methods of describing things. So our set builder notation is x, and this little vertical slash means you say such that x is an element in that little sideways E looking thing of all real numbers. And so that's just a way of saying all real numbers. And our range is going to be y such that y, I'm going to be careful about this, y such that y is less than or equal to -1. Okay, so that's set builder notation. Next, x-intercept. Well, we do not touch the x-axis anymore, do we? So there are no real zeros or real x-intercepts. So we will say no x-intercepts. And y-intercept, we have that's going to be the coordinate pair 0, -10, because we cross the axis. The y-axis is at -10. And if we don't see that apparently from the formula, but if we take that negative the negative sign times that negative 3 squared, we're going to get negative 9 minus 1, or negative 10. And the last thing, we're going to mention the vertex. Well, the vertex is right up here. At the point 6, comma, negative 1. And so I think that's all that we're being asked to do on this guy right here. Okay, next I'm going to go to problem 14. And this one from a table. So we're going to look at key values here. Well, first of all, we'll see if we can locate a vertex, because that's going to decide what our range is. So if we take we look at the y values, we see the highest value of y. You're looking for an absolute minimum or maximum. We have 9. So that's going to be our absolute maximum. So our vertex, I'm just going to put our vertex over here on the left, is going to be the point. The x value associated with that is negative 1. So negative 1, comma 9. And I put that here first because that's going to impact what our range is. Now we go to our notation, our domain. So our domain is going to be an inequality notation. X is greater than negative infinity. More room here than that. Put it like this to make sure I have more room. X is greater than negative infinity, but less than infinity. And our range is going to be y. Well, y, again, we have a maximum here. So our y is going to be greater than negative infinity. But we have our maximum of 9, but less than or equal to 9. And then in interval notation, we have our domain is all real numbers, which is greater than negative infinity, less than infinity. And our range is going to be greater than negative infinity and less than or equal to 9, which we seal off as a bracket. And set builder notation, domain, we have a little bracket here, x, such that x is an element of all real numbers. Now that's script R. And our range is going to be y such that y is going to be less than or equal to 9. Okay, and now a y-intercept, x-intercept. Well, what we're looking for, the y-intercept is where x equals 0. So right here at 0, 8, see x equals 0, so that's going to be the y-axis. So our y-intercept is equal to the coordinate pair 0, 8. Now for x-intercepts, we didn't have any in our previous problem. What we're going to have is where y equals 0. So right here at x equals -4 and x equals 2. So x-intercept, we have the coordinate pair -4, 0, and also 2, 0. And that should be everything We have a vertex and all these values here. Okay, let's go on to number 15. And the reason I have 15 here, I want to get 13, 14, 15, I want to get one of each. And so we're going to find from a function, algebraic function this time. And what I'm going to do is rewrite g of x and expand this to get a better look at things. So what I'm going to do is take this x plus 1 and expand it. And I'm going to do a little box thing over here on the upper right just to show you a simplified version we're looking at. We have x plus 1 and x plus 1. So we have x squared and 1x, and plus 1. So we get from that x squared plus 2x plus 1. And then we subtract 8. And so expanding out means distributing out, we get 2x squared plus 4x plus 2 and we have minus 8. And what this is going to do is give us a y-intercept. So we have combined like terms. We get 2x squared plus 4x and 2 minus 8 is negative 6. So that's our y-intercept. So y-intercept is the coordinate pair 0, negative 6. Now we're going to find the vertex. Fortunately, we're in vertex form, and in vertex form, what we have is it's the form f of x equals a times quantity x minus h squared plus k. And so the vertex is the coordinate pair h, k. Okay, so we can see this is vertex form. So our vertex in this case, x, it's x minus h. So we have to have x minus negative 1. So our h is going to be negative 1. And this negative 8 on the outside is going to be our y-coordinate of the vertex. And we have a is positive, so we have a parabola that opens up like this. Okay, so what it means is this vertex is going to be a minimum. So let's go do our domain and range. So our domain is going to be in inequality notation. X is greater than negative infinity, but less than infinity. And our range is going to be y is greater than or equal to negative 8, but less than infinity. In interval notation, we have all real numbers. And our range is going to be, we're going to have a minimum of negative 8 and we have no maximum. So that's our range. In a set builder notation, we have bracket x such that x is an element of all real numbers. We have our range. Y such that y is greater than or equal to -8. Okay, the last thing we need is our x-intercepts. What we're going to do is set g of x equal to 0. So I'm going to bring this vertex form down here and just kind of work that out. So we're going to say 0 is equal to 2 times quantity x plus 1 squared minus 8. And the first thing I'm going to do is add 8. So 8 equals 2 times quantity x plus 1 squared, and divide by 2. So we have 4 is equal to quantity, I'll leave a little room here, is equal to quantity x plus 1 squared. Now to solve for x, we're going to take the square root of both sides of this equation, and I'm going to come up here. And the square root of 4, and you got to be careful about this, because we take a square root, we solve using the square root method, we're not going to have 2, but we're going to have plus or minus 2. And that's going to be equal to x plus 1. So what that means is we're going to have 2 is equal to x plus 1, and also -2 is equal to x plus 1. And so if we subtract 1, we get x is equal to 1. If we subtract 1 over here, we get x is equal to -3. So our x-intercepts are the coordinate pairs -3, 0, and also 1, 0. So that's going to be all that. We got a y-intercept vertex. We got everything else right here. Okay, next. I'm going to go to this set here. We have 18, 19, identify and compare the x-intercepts. So I'm going to do 18, 20, and 22, and leave the viewer to do 19, 21, and 23. Identify and compare the x-intercepts of the two functions, and you have a linear function and a quadratic function. Well, the x-intercept we get by setting this equal to 0. So I say 0 equals 3 times quantity x minus 3. And if we distribute through like this, we get 0 is equal to 3x minus 9. And so if we add 9, we get 9 is equal to 3x divided by 3. We have x is equal to 3. So our x-intercept is the coordinate pair 3, 0. We only have one of those. Now I'm going to do similarly with this quadratic function, which has 0 is equal to quantity x minus 1 squared minus 4. And if we add 4, this is going to look a lot like that last one we were doing. We have 4 is equal to quantity x minus 1 squared, and we can solve by taking the square root. On the left side we get plus or minus 2. On the right side we get x minus 1. So what we have is 2 is equal to x minus 1, and -2 is equal to x minus 1. And then we add 1 to both sides, and we cancel out. We get 3 is equal to x. And this other equation here, we add 1, we get negative 2 plus 1 is negative 1 is equal to x. So our x-intercepts here are the coordinate pairs negative 1 comma 0 and 3 comma 0. And a takeaway from here is that you are going to have in a linear function only one x-intercept, but you can have 2 x-intercepts with a quadratic function. Next one, 20. We have h of x equals 2 times quantity x plus 3 squared minus 1, and g of x equals 2 times quantity x plus 3 minus 1. We want the y-intercepts. Well, for the y-intercept on this h of x1, what I'm going to do is I'm going to expand this x plus 3, so we get x squared plus 6x plus 9, and then minus 1, and then distributing, we get 2x squared plus 12x plus 18 minus 1, h of x. And then that's going to be equal 2x squared plus 12x plus 17. So what we have is now standard form. So our y-intercept is going to be the coordinate pair 0, 17. So that's that answer. Now for the other y-intercept, we're going to set that one equal to 0. 0 equals, and I'm just going to distribute right here, equals 2x plus 6 minus 1. So we get 0 is equal to 2x plus 5. And if we subtract 5 on both sides, I'm solving for an x-intercept here. I really want a y-intercept, don't I? That's a different thing. I'm distracted. Here's what I want. I still want to distribute. I'm going to say g of x is equal to 2x plus 6 minus 1. And so g of x is equal to 2x plus 5. So our y-intercept for this one is going to be the coordinate pair 0, 5. Okay, last one I'll do in this set is this 22. Identify and compare the domain and range. Well, domain is always going to be your all real numbers for each of them. So for this one here on the left, our domain is going to be greater than negative infinity, less than infinity. And the same for this one on the right. Domain greater than negative infinity, less than infinity. And our range is going to be, we have our vertex here at the point negative 4, 3. And so our range, and that's positive, so our range is going to be greater than 3, less than infinity. And that's for that one. Over here, we have the vertex, also negative 4, 3, but we don't have any inflection point here at all. So our range for this one is going to be also all real numbers. So a linear function has its range all real numbers, and a quadratic function will never have all real numbers as part of its range. So we have all our answers here, and That's our exercise set. I invite you to work all your other problems. Good luck, and thanks for viewing.